Ladies and gentlemen, dear colleagues, welcome. My name is Denis Hanzalek, and you are watching 55th talk of the scheduling seminar. Today, I'm happy to introduce Pieter Smet. He is from the Department of Computer Science at Leuven. He finished his PhD in 2015 on nurse rostering, supervised by Patrick de Kosmaker and Griet van der Berg. He's very active in Patat on both sides, organizing the conference and also participating regularly. And in general, he's interested in personal scheduling problems. Aside of that, he plays guitar and enjoys attending concerts, and he's a fan of music. So, Peter, it's nice to have you here. Please go ahead.
Yeah, thank you for the introduction. And of course, also for the invitation to give me the opportunity to talk a bit about my work. As you can see on the slide here on the title, my presentation will be about personnel rostering and then specifically on how we can generate what we call robust rosters that are suitable for dealing with disruptions caused by employee absenteeism. And I took a look at previous talks in this seminar series, and I actually noticed that there haven't been that many talks related to personnel scheduling, and I could not find one related to personnel rostering actually. So I'm happy that I can share some of my ideas and thoughts about these problems with you today. So I have divided my talk into 4 parts. So the first part will just be a general, let's say, introduction to personnel rostering to set the scene a little bit to establish some common terminology and so on. And then I will move on to the main topic of the presentation, which will be this robust, this proactive personnel rostering. And then in parts 3 and 4, I go a bit deeper into some recent contributions which we have made. The first one on trying to quantify roster robustness, and then finally looking into how we can leverage techniques from machine learning to generate more robust rosters. So that's the outline. I have to say that the presentation is not super technical. I did this on purpose in the hope, of course, that I can keep your attention until the end of the presentation. But I've added references throughout the slides, so you can always find more details on how specific things are done and so on inside of these papers. Okay, but we begin with personnel rostering. I won't spend too much time on trying to motivate why we are doing research on these types of problems. I think if you have talked to organizations in the past, you know that they are struggling with efficiently managing their workforce. For many organizations in many different sectors, it's hard to fill in their open job positions, to find skilled employees and workers and so on. And at the same time, it's also difficult for these organizations to retain their current workforce, right? You will find studies outside of operations research trying to explain why this is, especially since the COVID-19 pandemic. This issue has come to the forefront a bit more, but it has been ongoing for many years, actually. Now, I'm not claiming that personnel rostering or even operations research as a larger domain is the answer or the solution to all the issues in the job market. I think this is a bit of a bigger societal or economic problem, but from my experience at least, solving these kind of personnel rostering problems or other types of personnel scheduling problems, they can help organizations who are faced with very specific issues or challenges at the time, right? But okay, this is a bit of setting the context. These personnel rostering problems, what are they? So I will explain what this problem is, what their decisions, constraints, and objective functions typically are through a small example. So we are looking at a subset, or we are looking at a set of employees, I should say. So these could be employees who all belong to the same department or unit of an organization. And we have to assign them shifts or days off for a certain planning period. This planning period, in practice, this is typically 4 weeks or 3 months or longer, depends a bit. here on the slide, the example on the slide, we're looking at a planning period of 7 days, and just to keep it a bit manageable. So this is what you could call an empty solution, and then we can fill the solution in. We can assign some shift types or some shifts to these employees. So you see, employee 1, they start their week with an early shift. So the letter E stands for early in my example here. Then on Tuesday, they're again working an early shift. Then they are doing some late shifts, Wednesday to Friday, and then they have 2 days off on Saturday and Sunday. So when I'm talking about an early shift, a late shift, a night shift, this is also something which appears in this example. The shift here just defines a time interval during which the employee is expected to be at work, right? And to carry out the activities they are paid for by their employer. So that's the schedule of employee 1. Then employee 2, yeah, I mean, they don't have the same schedule, but it's looking very similar, right? They start with 2 days off, then some early shifts, then some late shifts. Now, of course, you can make these shift assignments, but you have to respect some constraints. And I would say one of the core fundamental constraints in personnel rostering problems, which you see across, I would say, all variants, have to do with staffing the shifts according to some demand. Yeah? And this is represented in the bottom part here on this bottom table. So here we keep track of how many employees we have assigned to each shift type on each day. So we have 1 person to the early shift on Monday, this employee 1, then 1 person to the early shift on Tuesday, also employee 1, and so on. So this is this first number in each cell. Then we have a slash, and then the second number. This tells you what the demand for this shift type on this day was. And then you see in this solution here, everything is fine. We assign the required number of shifts on each day, and actually there is one kind of exception to this situation, which happens here on Saturday for the night shifts. You can see that we don't require any night shifts during the weekend, but we have assigned 1 person to it, right? This employee 3. So this is a situation of overstaffing, which is usually not really preferred by the organization because you're paying people to work a night shift in this case, but there may not be a lot of work for them to do, right? So usually you don't want overstaffing in your solutions. You also don't want understaffing, which is even worse than overstaffing usually. And understaffing, of course, occurs when you need somebody in a certain shift on a day, but nobody is assigned to that shift on that day, which means that the actual service level can't be guaranteed by the organization and so on. So these are bigger issues than overstaffing, I would say. But in this situation, the staffing demand constraints, they're all looking pretty good. So when you're looking at constraints for the rostering problems, these staffing demand constraints or coverage constraints, you can also call them. This is an example of what we call a vertical constraint. Vertical because if you look at this kind of representation, it pertains to, you could say, the columns or at least some kind of vertical structure in this solution representation. There are other vertical constraints. You see constraints concerning the training of employees. You see constraints on the collaboration of certain subsets of employees. Maybe people want to work together in the same shift, or the opposite, due to whatever reason, they don't want to be assigned to the same shift. You also see this in practice, but I would say these staffing demand constraints, these are like one of the fundamental core constraints of rostering. So if you have vertical constraints, of course, there are also what we call horizontal constraints. And you can imagine what they refer to. They refer to a single row in this kind of representation, or they pertain to a single employee, right? So there are constraints on the assignments of a single employee, and we can further classify this large group of constraints in what we call counter constraints. So these are, in a way, relatively easy constraints between quotation marks, but just count the occurrence of a certain type of assignment, for example, throughout the whole planning period, and then limit this with an upper bound or a lower bound or whatever. So counter constraints are one thing. Series constraints, they restrict the consecutive assignments of an employee. And then successive series is a combination of two series where the first one imposes a kind of condition which should hold in order for the second constraint to actually become active. I mean, it's a bit poorly explained, but I have an example on the next slide to clarify this. And if you ask me, then I would say that these series constraints and also these successive series constraints, that these constraints are what make rostering problems, right? And if you would compare them to other types of timetabling problems, educational timetabling problems, and so on, in my opinion, it's these series constraints and successive series constraints which are really characteristic or unique. I mean, it's a big word, but let's say unique to personnel rostering problems. So this is kind of a general classification which we made some time ago. To make this a bit more concrete, I have an example here. So now we're looking at the assignments of a single employee for a period of 10 days. So they start with some night shifts, then they have days off on Thursday and Friday, then some early shifts and some late shifts. So just to give you an indication of what these rostering constraints are, right? These horizontal constraints, you could have a counter constraint, which limits the number of assignments per week. Full-time people need to work this many hours, 38, 40 hours per week. Part-time employees work less typically. You have series constraints which specify that you can work at most 5 days in a row. This is consecutiveness. You also have series constraints which says that if you have a day off, you need to have at least 2 consecutive days off. So if you would violate this minimum 2 consecutive days off constraint, you could end up with what is called an isolated day off, which means that a person could be working a stretch of days, then have 1 day off, and then could again work a couple of days afterwards. And this is usually not preferred by the employees because it does not really provide for sufficient recuperation. You don't have the concept of a weekend anymore in the sense of 2 days off. So this minimum 2 consecutive days off, this is also quite common, I would say. Weekends are also usually a special thing in these rostering problems. If you are assigned on a Saturday, if you have to work a shift on a Saturday, you also have to work a shift on Sunday. And ideally, it's the same shift. So this is the case in this solution here. This person is working an early shift on Saturday and Sunday. This is what they call a complete and identical weekend. This is also quite common. I'm not saying that all of these constraints hold in all organizations, but they are, as I say, common examples of rostering constraints. Then successive series constraints. This is also one of the core constraints. It's also one of the true legal requirements. Sufficient resting time between 2 working days, right? So usually you want 11 hours of rest between 2 shifts, which means, for example, that you can't do an early shift after a late shift because there won't be 11 hours of time between this. And then finally, another example of this successive series, which tells you that you should have at least 2 days off after having worked a stretch of night shifts, right? And this is again usually installed to ensure sufficient recovery time for employees who have been working in the night shift and so on. Now, these are all constraints. I haven't really talked about objective functions yet. What you see in models, if you read some papers on rostering and you look at their problem definitions, you will see that some of these constraints, these rostering constraints, are relaxed, right? They're modeled as soft constraints, and the objective function then simply becomes, well, simply is maybe the wrong word, but the objective function then becomes minimizing the number of violations of these soft constraints, usually in a weighted sum to give some priorities to different types of constraints. And this is not something which, how should I say it, people at universities do. This is also something which human planners actually do when they are constructing a roster. So this is a figure I took from a paper from some time ago, from 2014, but again, from my experience, it still holds today, by Robert Drake. And what he did, he went to a couple of hospitals and he looked at the rosters of different wards in these hospitals, and then he checked, okay, how many constraints are you actually violating with the rosters you are using? These were rosters constructed by people, let's say, not by algorithms, just manually constructed. And then the interesting thing to see in this graph here is that basically in every ward, there are at least some violations of rules. There isn't any ward that does not violate any constraints, right? So this whole concept of relaxing constraints and modeling this in a weighted sum of constraint violations, this is actually quite close to what's happening in practice. Now, the reason for these violations, often it's actually at the request of the employees themselves, right? Could also be due to the fact that some constraints are conflicting, and then out of necessity, yeah, you need to violate some constraints, and then preferably the one which is the least important, right? Which is also a difficult question on its own, which is the least important constraint, but okay. When it comes to algorithms, I have this slide here. So the table shown here I took from this website, which hosts one of the, I would say, more well-known benchmark data sets for personnel rostering problems. And the numbers in this table are not the thing to look at right now, I think. But what I want to show with this is that if you look into papers for personnel rostering, recent papers, you will find that you are actually able to solve really large problem instances, right? This data set has instances with up to 50 employees and a planning period of 6 months, or even a full year, sorry. Or instances with 100 employees and a planning period of 6 months. And we can basically solve them to optimality. So these are really, really big problems. You don't, at least I haven't really encountered this scale of problems often in practice. But still, you can find methods which can produce provably optimal solutions. And then looking into these papers more, you will find, in my opinion at least, 2 dominant algorithms or 2 dominant approaches. You have, on the one hand, exact algorithms based on branch and price. So these kind of methods work generally quite well for rostering problems. And on the other hand, you have meta-heuristics based on local search, large neighborhood search, which are also quite performant for these types of rostering problems. Of course, I'm generalizing a lot here. I'm sure you can find papers out there for very specific variants of personnel rostering for which a completely different algorithm performs very well. But in general, at least this is my view on the whole state of the art for personnel rostering algorithms, at least. Now, what I talked about up until now about these rostering problems, these are solved in practice actually a long time before the real planning period begins. So I have this small illustration here. Suppose we have our planning periods which we want to construct the roster for. We have to do this actually several weeks or months before the start of this planning period. So solving a roster, constructing a roster from scratch, from zero, this happens a long time before the planning period starts. I can tell you in Belgium, for nurses in hospitals, for example, they need to receive their roster 3 months in advance. This is a new, some new legislation which came, which became active 1 or 2 years ago. And 3 months is, of course, a long time, right? A lot can happen in 3 months. A lot can happen during the planning period as well. And when unexpected events do happen, when disruptions do occur and cause infeasibility to your nicely constructed roster, that's when we enter re-rostering, right? Or reactive rostering. And this is the problem of actually repairing infeasibilities which are caused by disruptions due to uncertainties which exist when you're dealing with humans, right? Or just in service industries in general. So that will be the next part of the presentation, this reactive and then coupled to it proactive rostering. So reactive rostering. Suppose we have our nice roster from before. So this is constructed 3 months in advance. But then the actual planning period begins. And what do we see? Employee 2 becomes absent on this Wednesday. And this causes a bit of an issue because employee 2 was assigned the early shift. So now we have a situation of understaffing. There is actually nobody on Wednesday to staff the early shift and to carry out the activities which are required at that time. Yeah, so this is an issue. Then with reactive rostering, we want to resolve this infeasibility. So what do we do? Well, the only employee who isn't working on this Wednesday is employee 3, but we can't assign an early shift to employee 3 because they are working a late shift the day before, right? And then we are not providing sufficient resting time between 2 days, and then we have basically another infeasibility. So what we do is we, in this case, assign the early shift to employee 1. Now, employee 1 was assigned the late shift, so now we need to move the late shift to another employee, let's say to employee 3. But now employee 3 is working 6 days in a row, which is also not good. So what do? We break this stretch of consecutive working days by moving their night shift to employee 4. And then you could say we have restored feasibility, although now you see we have this isolated day off for employee 4, which may also not really be desirable, but at least it's better than all of the other constraint violations we would have occurred otherwise. So to repair this infeasibility, let's say, caused by the absence of employee 2, we have created this kind of chain of repair operations consisting of 4 steps to restore this feasibility. Now, if you look into the literature, you will find papers who are presenting algorithms to basically construct these kind of repair chains or repair steps, right? Yeah, these are these re-rostering methods, these reactive rostering methods. And I would say a few common elements which are shared among most approaches which solve this kind of problem are that they are typically considering alternative objective functions, or at least they are including also a term which tries to minimize the number of changes you actually have to make to repair the infeasibility, right? They are minimizing the number of perturbations to your roster necessary to restore feasibility. Also some constraint relaxations, so maybe by relaxing some constraint or removing some constraint, you can limit the number of repair steps you need to restore feasibility. And then finally, also strategies to limit the search phase. So this is a bit more technical on the algorithm side. But this, well, the way this is done is, for example, by only allowing changes on a few days until a few days after the disruption has occurred. So just to ensure that you aren't making changes towards the end of the roster as well, but to limit like the area of the roster where you are making changes. And similarly, you could restrict the set of employees which you can change during re-rostering. These are these kind of strategies. There are a bunch of papers on this. There is one reference here on this slide, which has quite an extensive computational study, but you can find others as well. Now, the thing with this proactive rostering, even if you have a very nice algorithm which minimizes the number of perturbations, is that typically you still need some kind of last-minute change to your roster for employees, right? You will still modify assignments. You will change, in the example, late shifts to early shifts. You will change days off to regular working shifts and so on. There have been several studies which have tried to figure out what the impact of these kind of last-minute changes are for employees, and the results are quite consistent in the sense that they're all negative impacts, right? Whenever you are changing the roster of an employee and the employee assumes that the roster was what it would be, this has a negative impact on their health, on their job engagement, and so on. So this reactive rostering, it can work, but inevitably it has some negative impacts. So what would be better? And then we are entering the domain of proactive rostering to construct your rosters in such a way that they can better tolerate these kind of disruptions caused by employee absences, right? You will find in the literature many different ways of doing this. In this presentation and in our work, we focused specifically on proactive rostering methods which make use of buffers. Now, these buffers, there are 2 types. Okay. there are two types which we considered in our research, which I will explain on the following slide. So the first type of buffer, which you can use in proactive rostering, works as follows. So here we have again constructed our roster, let's say 3 months before the planning period starts. It looks a bit different, but the most important difference is that we now have assigned 2 people to the early shift on Wednesday. So here we have a case of overstaffing, but of course, if your or if our employee 2 now becomes absent on Wednesday, this overstaffing gets reduced or disappears, and you are actually left with a nominal staffing level on that day. So this is what we call a capacity buffer. I mean, conceptually, it's quite easy, right? You just assign surplus resources for certain shifts on certain days, and that's it. That's how you install this kind of capacity buffer to ensure your roster is more robust. And the nice thing about these capacity buffers is that you don't actually need to do any re-rostering. The person is already there. You have assigned 2 people to your early shift during the rostering phase, and you don't have to do any re-rostering when employee 2 becomes absent here. So that's quite a nice approach. This is one way of doing it, one type of proactive rostering. The second type I will be discussing also makes use of buffers, but works a bit differently. Instead of assigning a capacity buffer or installing a capacity buffer on Wednesday for the early shift, now we assign a special type of shift to employee 3 on Wednesday, namely a reserve shift. So a reserve shift is a kind of on-call duty. And when an employee is assigned to such a shift, this means that they have to be on standby, right? They don't have to come into the workplace, but they know that they can receive a call telling them to come in to cover for some absence and so on. So when employee 2 now becomes absent, what happens is during the re-rostering that the reserve shift is converted to the early shift in this case. So here a re-rostering operation is necessary, but of course the impact is not as big because this employee 3 he knew that he was on standby, right? The reserve shift assignment was part of his assignments, which he got, let's say, 3 months before the start of this period. So just to compare them, these capacity buffers and reserve shift buffers. So capacity buffers, they are just part of the regular assignments, no re-rostering required. But of course, the big downside of this type of method is that they're not very flexible. This type of buffer is not really flexible in the sense that you can only cover for absences of the same shift type. If in this small example of the capacity buffer, employee 1 would have become absent, yeah, then I mean, it's not much use to have employee 3 doing an early shift, right? You would still need a re-rostering operation to change the early shift to a late shift and so on. So it's not very flexible, but it's part of the regular assignments, which is a good thing. And then these reserve shift buffers, on the other hand, they do require a change during re-rostering, but they are much more flexible, right? They can cover basically for absences in the different shift types as well. So looking at the re-rostering operations, without considering buffers, we can do these actions, or we can make these type of changes during the re-rostering, basically. So we can change an existing shift assignment, converting a late shift to an early shift, a night shift to a late shift, and so on. We can change a day off to a shift, which is worse generally. Or, and this is has the highest cost, let's say, you can call in external employees to staff whatever shifts you need to have. But this usually is really not preferred because well, there are applications where this is not so trivial, right? Where you need specific training and so on. So this could be very costly for the organization. However, when you use these types of buffers, you have some kind of additional re-rostering operations which you can use, being just using employees in the capacity buffer, which has no re-rostering cost. Of course, you have to pay these people, right? When they are, when you assign somebody a shift, usually you have to pay them. So in that sense, it does incur a cost, but at least during the re-rostering, there's no additional cost of using these people in the capacity buffer. And then converting a reserve shift to a regular working shift. This is a re-rostering operation which incurs a small cost, or at least a cost which is smaller than changing a regular shift assignment. So this is the very briefly, of course, the whole idea of this reactive proactive rostering. And it's in this context that I would like to talk about a first contribution we made. And very briefly, the idea of what we tried to do was to come up with a kind of metric which you could use to measure how robust a roster actually is, without having to rely on doing simulations of absences and re-rostering and so on. So that was the idea. So this was joint work with Tony Wickert, who was a PhD student at KU Leuven at the time, and Greet van den Berge, who is professor at KU Leuven. So, as I said, the idea was to develop this kind of metric of roster robustness. And we ended up with a kind of, let's say, function that you can apply to a given roster. And this function, what it returns is a value, which when it's very small, let's say close to 0, it indicates that the roster is not very robust, that very few of the working shifts can be replaced. On the other hand, higher values indicate that many or all of the working shifts can actually be replaced. And we defined this metric at different levels of granularity. So we defined the metric which tells you something about the robustness of the roster as a whole, but then we also defined a variant which could tell you, okay, given one day in my planning period, how robust is this single day? And then also at finer levels of granularity, right? At the shift level or even at a skill level. Now, I won't go into too much detail on how these metrics work, but I have one example here. And the main point I want to bring across by showing this example is to make clear that it's not very complicated the way we set it up, which I think is an advantage, actually. So suppose we want to measure how robust our roster is, and specifically we want to measure robustness, which comes from installing reserve shift buffers on a certain day. And so this is this kind of daily level. So what we do is we just count the number of reserve shifts assigned on that day, and we divide it by the total number of working shifts assigned on that day. And this gives you an indication of the kind of robustness you have for that day coming from reserve shift buffers. Now, since this metric is so simple, what this allowed us to do is to actually use it as a constraint and then say, okay, now let's generate a roster which has at least this robustness level. And this is exactly what we did in this paper. We modeled the rostering problem we were looking at the time as an integer programming problem. And we added a constraint which basically says, okay, I want to have a robustness level of at least this percentage. And then by varying this percentage or this minimum robustness level, you can actually figure out, or using numerical experiments, when it's no longer beneficial to increase roster robustness. But I have a small example of what I mean by this in the coming slide. Well, in 3 slides, actually. So our computational study, just to give a bit of information about this, what we did is we took data from a well-known data set from personnel rostering, the one used in the second international nurse rostering competition. So the instance we selected had 35 employees, 4 weeks, and so on. And then we made 2 variants of this instance, basically. One where the employees, one without any skills, which was nice because this meant that there was a high degree of substitutability between these employees, right? You didn't have to account for skills. That made it a lot easier. And then another variant in which the employees had skills. And these skills were organized in the kind of hierarchical manner, meaning that employees at the top of the hierarchy, let's say, they could substitute for employees below them. And then employees at the lowest level, they could only substitute for absences or for employees who became absent, which were situated at the same skill level. So this imposed this kind of additional constraint which you had to consider during the re-rostering, which really limited the number of possibilities you had during re-rostering, actually. So what we did is, in our computational study, to get a kind of, to get the real cost of re-rostering, is we generated a bunch of what we called absence scenarios. So these were basically just scenarios in which we generated some employee absences. And for each of these scenarios, we applied a re-rostering method and then recorded what the cost was. So the re-rostering was also done with integer programming and also to optimality. And then the different robustness levels we looked at were, well, they're shown on the slide, right? They vary from 0% to 10%. 0% being no robustness at all. So if you generate a roster with this, then basically there are no buffers installed. That's what it comes down to. It doesn't go higher than 10% because we are limited by the number of employees we have. So we only have 35 employees. We can't create any more employees. So if you wanted to have high robustness levels, we would need to have more employees to assign to these buffers, basically. But this was not possible, so that's why it stops at 10%. Now, to measure, let's say, the quality or the cost of the rosters we generate, we used two values, being the rostering cost and the cost after re-rostering. So you can see on the slide that where both of these costs come from. So the rostering cost is basically the cost you obtain when you construct the roster initially, so a long time before the actual period starts. This is where you already put people in the buffers and so on, based on the metric, the value you impose. And then during the planning period, people become absent. You need to do re-rostering, and this leads to a cost after re-rostering or a re-rostering cost. So what do these costs consist of? The rostering cost basically has components which represent the wage costs of the assignment or the employees you use in the solution in your roster, and also some term for understaffing, which represents basically the cost of using external employees, right? And then the cost after re-rostering consists of, well, all the costs you had to pay during the rostering phase, plus, and this is the important part, of course, the costs which come from making changes necessary to restore feasibility. And then we compared the rostering cost and the cost after re-rostering. So in this paper, you will find many results. It's quite an extensive computational study. I will not discuss all of them. Instead, I have selected one plot from that paper, which I think is quite nice and also intuitive in a sense. So what we show here is for different minimum robustness levels, we show the rostering cost, which is the blue bar, as well as the cost after re-rostering, which is this pink bar. And then when looking at the re-rostering cost, you see, when looking at the rostering cost, the blue bars, you can see that it increases as we require a higher robustness level in our rosters. And this is really intuitive. You don't really need a computational study to understand this, of course, because if I say I want a higher robustness level in my roster, this means putting more people in these buffers, which means paying more wages, basically. So it's really not surprising that the rostering cost increases in this way as we also let the robustness level increase. However, the re-rostering cost, the pink bars, they of course show a bit of a different trend. There you see that if we increase the robustness level, that the re-rostering cost drops, right? Initially, it reduces, and this shows you that, of course, I guess the most important thing that this demonstrates is that installing these buffers actually works, that this metric we have developed, that it actually measures robustness. I think this is the most important conclusion that you can draw from this, but there are other things to see as well. So initially it drops, but you also see that as soon as we hit this 7.5% roster robustness, it kind of converges, right? And even if we require 10% robustness, the cost slightly increases, the re-rostering cost slightly increases. And this tells you that at this point, 10% roster robustness, that this is too much, right? At this point, we are putting people into these buffers who are not really used during the re-rostering. Of course, a big note to make here is that it all depends on your computational study. I think here we simulated absences using an absenteeism rate, which we got from an HR agency in Belgium that tracks this across sectors for many different years. If you are looking in a different country, for example, or a very specific sector where the absenteeism rate is much higher, then probably these pink bars will show a different trend, right? Then probably it will still make sense to increase up to 10% roster robustness. You will still see the re-rostering cost dropped. But in our computational setup here, we observed this. Now, this is all very nice. And as a manager, I think this would be quite interesting because you could use these kind of results or even this kind of plot specifically to see, okay, what is my ideal kind of robustness I need in my roster? At which point am I not putting too many or too few people in these buffers? Now, the downside is, of course, that you need a kind of expert to answer this question or to, well, interpret this plot, but also construct this plot, generate the data, and so on. This is you need somebody who knows what they're doing, right? So this is a bit of a downside of this whole approach, and this made us think: how can we do this in an alternative manner? And specifically, how can we leverage techniques from machine learning to generate generate rosters that are sufficiently robust? Actually, that's the question. And then we ended up in this quite, let's say, straightforward or simple predict then optimize approach, which works as follows. First, we built a machine learning model which can predict absences, right? Well, I say this, but of course, it's a huge amount of work to do this. And then we use these predictions to determine how many reserve shifts we should have in our roster. And this basically becomes a parameter in a constraint of our rostering problem. And this is all easy. We solve this with an algorithm, and we have a robust roster, which is which installs a number of reserve shifts based on predictions you made, which come from historical data, ideally. Now, the thing with this approach, with this whole idea, is that the actual robustness of your roster you generate depends on how well your machine learning model can make predictions, right? And then a very natural question that arises is, okay, but how accurate does my machine learning model actually have to be in order for my resulting rosters to be better than just rosters constructed with a very simple policy, which assigns, for example, 1 reserve shift per day or something, or 2 reserve shifts per day, right? Which kind of prediction performance do I need to reach in order to be able to outperform a very simple, robust rostering policy? So this is not an easy question to answer, in my opinion. Of course, you could say, I don't care about this question. I will just try to train my model as good as possible and then see what happens. But of course, there's a cost associated with this, right? Training these models, this is not for free. So that's why we thought that this was still a kind of a valuable question to try to answer. What would be the required performance be of a machine learning model in this kind of approach for it to be able to outperform a simple, robust rostering approach, which does not rely on machine learning or even rely on data at all? And that's, as I said, the question we set out to answer. So this was joint work with Martina Doneda and Giuliana Carello from Milan, Ettore Lanzaroni from Bergamo, and Greet van den Bergen from Leuven. And I should say it's still quite work in progress, but I thought it would be interesting to share it with you anyway. So how does this work? Well, we start from setting a certain prediction performance level of the machine learning model which we want to evaluate. We set it ourselves. So this is a bit strange. Usually, the way you would do this is to train a model and then see what the performance of this model actually is. But we kind of change this order, and instead, we start by setting the performance level which we want to evaluate, the prediction performance level which we want to evaluate, and then we actually simulate the predictions that a model at this performance level would make. So at no point in our research actually have we trained a model so far. Instead, we have just simulated what the predictions would be made by a model that has a certain performance, which we set. So we simulate these predictions, which gives us the number of reserve shifts per day, right? This is this predict and optimize approach I showed on the previous slide. Then we use this number of reserve shifts to generate our robust roster. So this is all good. And then we evaluate the re-rostering cost of this robust roster. So to determine this re-rostering cost, we basically did the same as in the previous research. We run a bunch of simulations. And for each simulation, well, each simulation actually consists of a number of employee absences, and then we do some re-rostering, and we record what the re-rostering cost was. So at this point, you have a re-rostering cost, which you obtain if you would have a machine learning model that can make predictions with this accuracy. And then you can ask the question, okay, am I happy with this re-rostering cost? Happy is a bit of a strange term to use, maybe. The threshold we set is this re-rostering cost better than a re-rostering cost we would obtain by just assigning 1 reserve shift on each day or 2 reserve shifts on each day. Just a robust roster obtained with a non-data driven policy. If your re-rostering cost is lower than this threshold, then you're happy, right? Then you can set out to collect your data and train your machine learning model. And when you reach this performance level, you can be safe and you can generate your robust rosters. And you know you will improve upon something non-data driven. However, if your re-rostering cost is higher than this threshold, is worse than a non-data driven approach, then what we would do is we would just reiterate this whole loop. We would update the performance. We would make simulated predictions at a higher performance level, at a higher prediction performance. And we would reiterate this loop until we arrive at a re-rostering cost we are satisfied with. And this kind of gives you, following these steps, gives you an answer to the question I posed 2 slides ago. So in our case, the machine learning model which we used was actually a binary classifier. So we used true positive rate and false positive rate to characterize the performance of this simulated machine learning model. And then what we did in our computational study is we varied these 2 performance metrics, so true positive rate, false positive rate, and we filled in basically this whole table with the re-rostering costs we obtained at each performance level of the machine learning model. So we simulated predictions at a true positive rate of 0, but there should be an additional column, I think. At the true positive rate of 0 and a false positive rate of 0, we simulated predictions at a true positive rate of 0.1 and a false positive rate of 0, and so on. And each time we recorded what the re-rostering cost was, we filled in this whole table, and then we drew conclusions based on what we saw, which I will discuss in the next slide. This will make it a bit more specific. So for this study, we used basically the same data as in the previous study. So this one instance from the second international nurse rostering competition without skills, and then also a variation of this instance, which had these hierarchical skills. So again, I did not add every plot we have until now, because this would take way too much time to explain, but I've selected a few ones which I thought were quite interesting to see. So this plot is basically the table I showed on previous slides, which was empty but filled in. I'm not showing the specific re-rostering costs we obtained in numerical values, but it's shown as a heat map. just to make it a bit more visually interpretable. So the red colors, when the color is red, this means that the re-rostering cost is high, which is not what we want. When it's green, this means that the re-rostering cost is lower. And then you see what re-rostering cost we would obtain if we would have a machine learning model with this certain with a given prediction performance. There are several things to see in this slide, but I think I have to hurry up a little bit. So we obtained the lowest re-rostering costs when our true positive rate was 1 and our false positive rate was 0, which is what you would expect. Nothing too unsurprising there. What was kind of surprising was that if the true positive rate is quite low, then we could improve the re-rostering cost by increasing the false positive rate, which is kind of, or we found it at least not very intuitive. We have a kind of hypothesis to explain this. And our idea is that if the true positive rate is low, you will actually predict few true positive, you will make few accurate true predictions, right? Which means there will be few reserve shifts included in the roster. However, if your false positive rate is higher, you will actually predict many absences and you will include reserve shifts. Okay, they are false predictions, but they still result in more reserve shifts in the roster. Maybe they're on the wrong day, but apparently the re-rostering can still make use of the flexibility in the roster due to these reserve shifts to end up with a lower re-rostering cost, which was not too intuitive at first, but this is our current explanation for this. So in general, I added it here. It seems that it's better to be conservative and to actually assign too many reserve shifts than too few. But again, there's this tipping point, right? Now, this is just looking at absolute values at really what the re-rostering cost is. We also compared the re-rostering cost of this data-driven approach to the re-rostering cost we would obtain with a non-data-driven approach. And this is what is shown here. So these values are actually the ratio of the re-rostering obtained by the data-driven method over the re-rostering obtained by the non-data-driven method. So when this value is 1, which is indicated by this red dashed line, by the way, this means that both approaches result in the same re-rostering cost. They're equally good or bad. When the value is lower than 1, which are these green areas, the dark green areas, this means that our data-driven approach is better, and when it's red, the non-data-driven approach is better. And then you see that we can actually outperform this non-data-driven approach under, I would say, reasonable conditions. If we have a true positive rate higher than, 0.55 or something, then we can actually outperform this simple non-data-driven approach that assigns 1 reserve shift per day. We also compared it to different policies which assign more reserve shifts per day, and then it changes a little bit. This was all for the case in which there were no skills. When we do consider skills, these hierarchical skills, the situation becomes a bit different. Actually, there are situations where our data-driven approach can never outperform the non-data-driven approach, which was also interesting to see. But yeah, I won't go into too much detail due to the time. Then to conclude, I will go over this quite quickly just to indicate what some interesting questions are maybe. So when you are doing the re-rostering, I think it's quite interesting to spend some time on trying to model the true impact of re-rostering, not just counting the number of changes, but also the impact on well-being, job engagement, health, and so on. Exploring other types of roster robustness. I limited the presentation to these capacity buffers and reserve shift buffers, but are there other ways, especially when you have these skills, cross-training, and so on? I think is quite promising. And then this whole idea of evaluating the machine learning performance requirements, these prediction levels, trying to generalize the simulated machine learning methodology, which is something we're currently also doing. I think this is also quite interesting. I have a final slide, which will take 10 seconds, with a more general outlook concerning research and personnel scheduling. I think in general, the focus is shifting a bit more towards ensuring employee well-being by, for example, considering reliability. So this has to do with robustness, right? But also trying to increase the autonomy of employees in the roster construction process, and also ensuring fairness at all different levels, of course. I guess due to whatever societal shifts we see, this is really a nice thing to focus on in the future. And with that, I finish my presentation. So thank you a lot for your attention. And I guess now there is some time for a discussion. Hopefully there is some time left.
Okay, so please ask questions, or you can say some remarks you have. You should be able to unmute your mic yourself. So if anybody wants, just try. Before you start, maybe I can ask the first question. For those reserve duty, do you also consider some specific constraints, like placing such duty at the end of a consecutive sequence of shifts, or something that is maybe preferred by the employees, that it doesn't really, if you have 3 days off, that it is not in the middle or something like that?
Yeah, I didn't explicitly mention this. So the we limit the number of reserve shifts that can be assigned to a single employee. So you don't want one person to be working all the reserve shifts, right? This has to be spread out a bit across the different employees. So this is one thing. And then for the rest, and this is quite interesting actually, the rosters are constructed in such a way that the reserve shifts can be converted to any shift type without violating any of the horizontal constraints. So this means that these reserve shifts are positioned such that, for example, whether you convert them to an early shift, a late shift, a night shift, whatever, you will never violate, for example, the 11-hour resting time constraint between 2 days. This is just part of the roster construction process. So this is done by specifying these constraints in a specific way, of course.
But that's relatively complex, because you have to consider different alternatives. On the type of shift and so on. So that's really interesting.
It is complex, and I think it's also quite restrictive in a sense. If you would allow some violations, then I guess there are more places where we could put these reserve shifts and so on. It would be easier to assign them.
And so the reserve shift is kind of on-call duty when people should be close to their workplace, so they can reach it in reasonable time, and they should be on call, so ready to pick up the phone and react quickly, right? That's it.
Yeah, indeed.
Okay, so any other question? If not, thank you very much, Peter. It was very informative and I think very comprehensive talk, surveying many different parts of personal rostering, from very early description up to such concepts as machine learning. Thank you once more. It was excellent. And now let me mention the talk which we have in 2 weeks. It will be given by Andrea Rossi from University PSL. And he will speak about maximizing stability of assembly line balancing schedules under uncertain task duration. So hope to meet you in 2 weeks, and stay with us. Thank you very much for being here today, and bye-bye. Hello, Andrea.
Bye-bye.
Bye-bye.
Thank you, Peter.
Bye-bye. Thank you. Bye-bye.
Thank you for a nice talk. Bye-bye.
Bye. Thank you.
Bye.